Okay, so again, the important thing here, guys, is being able to tell the difference between the different types of questions. Okay, number one is what kind of a question? It's a work energy theorem question. Okay, and number two is a law of conservation of energy question, right? We got to be able to tell them apart. Okay. All right. So for number one, give them a mark for their givens. Okay. The mass of the small cart was 1.5 kilograms. It was initially traveling at 3 meters per second, but a force acted on it that caused it to accelerate to 9 meters per second. Right. And we said several times that looking for the word or seeing the word force in a question is usually an indicator that it is not a law of conservation of energy question, but is in fact a work energy theorem question. The other way we know it's a work energy theorem question is the energy of this object clearly does what? Work is a change in energy. Does the energy of this object change? It does, okay? But the energy of an object in a law of conservation of energy question does not change, all right? Okay, their next mark, identifying it as a work energy theorem question, so hopefully they had that somewhere. They may have indicated that it was a change in kinetic energy, and that would be fine. Okay, if they have something like what's circled here, okay, where they showed that that's final kinetic minus initial kinetic, okay, you can give them a mark for that. All right, because we're looking for the amount of work that's being done here. Another mark for plugging in the numbers. So 1/2 times the mass, 1.5, times the final speed, 9, okay, which is squared, minus the initial kinetic energy, 1/2 times the mass times the initial speed squared. And when we do that, okay, we should get a final answer of 54 joules. Okay, questions on that one? Okay, second question, they have givens of some kind written out. Initial height was 35 meters. Our final height was 12 meters. And our our final speed was 21.8 meters per second. So we do know right down here that it's moving at 21.8 meters per second. What we don't know is how fast was it moving up here at the top of the hill. All right, so we have to assume then, since we're being asked to solve for that, that it does have some kinetic energy at that point. Okay. All right. So our next mark then is for identifying this as a as a law of conservation of energy question. So if they have either one of those two things, okay, you can give them a mark for that. It does have, okay, and the importance obviously of this step here, guys, I know a lot of people on exams skip that step, and if you do, okay, but the importance of that step is to identify what types of energy it has at all the points, okay? I identified that it had potential energy at the top because it's 35 meters off the ground. It has kinetic energy at the top because they asked me to calculate speed and I have to assume it has some, okay? It is off the ground at the end, so it has potential, and it's moving at 21.8, so it has kinetic, okay? So that just helps me to identify if I have them all or if there's any that I can cancel off early. Okay, next mark, plugging in the formulas. So for potential energy, m times g times h initial. For kinetic energy, 1/2 mvi squared. Final potential energy, mghf. Final kinetic, 1/2 mvf squared. What can I cancel off of there? Mass, which is good because I don't think I gave it to you in the question. All right, so you get rid of that, and you're left with this. So 1 mark for this, either one, okay? Then we got to manipulate for VI. Okay, so we're looking for this one right here. So the first thing I'm going to do is subtract GHI over to this side. Okay, and then I'm going to divide by the 1/2, and then I'm going to square root, and that's going to leave me with this. So if they have that, you can give them another mark. You can give them a mark if they plugged in their numbers correctly. 9.81 times the final height of 12 plus 1/2 times the final velocity or final speed, sorry, of 21.8 squared. Okay, minus the initial potential, 9.81 times 35 over 1/2. And give them their sixth and final mark if they got that it was moving at 4.90 meters per second at the top of the ramp. Make sure they have units on their answers. If they don't have units on their answers, they are not right. Okay, units for the first question were joules, by the way. Okay. So a mark out of 11, please. Let them see it, and put it in the box. All right, first bit of details. There's 20 multiple choice questions. Okay. And they range in topics. Okay, there's a fair amount of things about thermodynamics. That's probably the biggest thing in the multiple choice, simply because that's a lot of recall. Okay, there's also a little bit of kind of situational type multiple choice questions about thermodynamics, like, you know, here's a situation, which law of thermodynamics is best illustrated by this, or, you know, things like that. So, you know, or which system is being described here, right? Stuff like that. So there's a fair amount of stuff on thermodynamics in the multiple choice. There's a couple of V equals D over T problems in the multiple choice, just because they're quite simple and they're not really worth wasting a problem on, okay, in the written part. So there's a couple of those. There's one acceleration question in there. And there's 3 or 4 graphing questions where you'd be asked to interpret a graph. Not necessarily, I mean, there might be a calculation in there, but mostly it's just interpret. Okay, and then there's a couple of things about work and energy. And 2 questions about efficiency. Right, so that's kind of the topics that'll be covered in the multiple choice part of your test. Okay, now for the written response, okay, for the written response, we've got 7 questions in total. Okay, and written response on a physics test is like problem solving. Okay, so it's not like writing out a paragraph per se. All right, it's going to start off with a graphing question. Okay, and then it moves to acceleration. Then graphing again. Now, how many types of graphs did we go over? 2. Position versus time and velocity versus time. I guess that probably means there's 1 of each. Okay. Okay, so expect you're going to have to do the types of calculations we did in class, okay, on there. Yeah, I told you this yesterday. There were 2 work energy theorem problems. Okay, number 6, the law of conservation of energy. Number 7 is the thinker. I'm just going to tell you that. It's just the thinker. There may actually be more than one way to solve it even. That's kind of the, let's say, the cream of the crop question. Okay? Yeah. Right. Tells you whether you really know this stuff or not. Okay, and as a result, there's more than one way to solve it. Okay. Question? Oh, I thought I saw your hand going up. All right. So, are there any questions from the review sheet that you want to go over, or any questions at all? Okay, for the unit that you want to ask. Okay. Well, if more come up, okay, don't be afraid to ask. I'll come up here and I'll do them on the board for you. Okay. But what you should be working on right now is anything and everything to do with preparing for tomorrow. If you have not done the review package, that would be my recommendation. If you have done the review package, then you've got worksheets, okay, that you can look over. I would say pick a few questions at random off of there, okay, and see if you get them. Look at your graphing stuff, okay, for sure. Look at your 2 labs, okay, that kind of stuff. And if you got questions, just ask. Okay, so let's say with graphing here, guys, let's look at position versus time graphs first. Okay, so we got meters and seconds most likely on this graph, and let's say, we've got a graph that goes maybe something like this, and then over, and then up, and then down. Okay, so let's just say that this is, I don't know, 6, 8, 1, 3, 6, 7, and 8. Okay, we'll say something like that. Okay, just so we got numbers. All right. If I asked you calculate the total displacement over the whole trip, how would you do that? Right. This is a position versus time graph, guys. I got to remember that displacement is final position minus initial position, and I can read position right off of this graph. Okay? That's why I caution you against memorizing, oh, area under the line is displacement. That only applies to one kind of graph. The area under the line on our force distance graph in our work lab was work. Okay? The area on a graph is a different thing. The area on this graph is meaningless. It's meter seconds. I don't even know what that is. Okay, you find the area underneath this line, you're multiplying meters and seconds and you get meter seconds. I have no idea what that measures. Okay, as far as I know, it doesn't matter anything. Okay, so don't do that. It's not the right thing to do on this graph. Okay, you look at this graph and you go, it's a position versus time graph. If I want to find displacement, final minus initial is what my formula sheet says to do. I can get those off of this graph, right? So I would go 1 minus 0, and my total displacement would be positive 1 meters. Everyone follow me there? All right, what if I asked you to calculate the velocity between 7 and 8 seconds? You guys are obsessed with this area shapes thing. Okay, guys, if I want to calculate velocity, velocity is displacement over time. Okay? Can I find the displacement between this position and this position? Yes, the displacement is that it goes from 8 to 1. So that's negative 7 meters. And how long does that take? 1 second. What's the velocity? Negative 7 meters per second. Okay? Don't memorize. Look at your graph, look at your formula sheet and say, how can I get this? Okay? How can I get what I'm being asked for from this graph? Okay? Everybody follow me there? All right. What if they asked me to calculate the total distance traveled? Okay, see where it begins and where it stops is part of it, yeah. Does distance care whether I go forward or backward? Then I need to know how far I go in each part, right? Okay, so how far do I go in this first part? 6. How far do I go here? I don't go anywhere, right? Because it starts at 6 and ends at 6. So, okay, how far do I go here? 2, and here we said just a minute ago was 7. So, how far did this thing go? 15 meters, right? 8 plus 7 is 15, yeah? Okay. Or 9 plus 6, whichever way you want to do it. Okay, it's 15 meters. That's it. Now, what if I wanted to calculate the average speed over the whole trip? Not total displacement. I'm not looking for speed. Total distance over total time. Okay, I just calculated that. It was 15 meters. How long did this trip take? 8 seconds. So, well, that's going to be like 1.9 or so, okay, meters per second. All right, do I need a vector on that? No, speed is scalar. See how important it is to know which things are scalar and vector? Okay, I ask you for a vector quantity, I expect a vector. I ask you for a scalar quantity, and you give me north, I'm going to go, wrong. Okay, yeah, because that tells me you didn't know that speed was scalar, and that was important. Okay, is that making sense for the position time? All right, velocity versus time graph. Okay, I want to know the acceleration in between 0 and 5 seconds. Okay, I've got a formula that says do this, okay, and I could do that for this section of the graph. Now, if the graph was a bunch of points and I had to draw a best fit line, then I wouldn't be able to do that. I would have to then find what? The slope of the line, because that's where that formula comes from. Okay, in a case like this where I have multiple sections, I can just do VF minus VI over T, because that's all I'm going to have. All right, so for this one here, we'll have our 5 minus 10 over 5. So we're looking at negative 1 meters per second squared as our acceleration during that phase. Everyone with me there? Again, it's not a matter of memorizing, it's a matter of this graph is showing me velocity and time, and I'm asked to find something. So you go back and forth to your formula sheet and you see, here's some things that are on this graph. I might be able to use this formula to solve something about this graph. Okay? All right. What's the acceleration between 5 and 15 seconds? 0. Okay? Everyone follow me there? Now, I shouldn't see any calculating if I ask a question like that on a test. You wouldn't believe what I've seen when I put a question like that on a test for people trying to show me that there's an acceleration during that phase. They go through like 8, 9 marks worth of calculating to prove that they're wrong. Okay? They wind up with some answer at the end instead of going, well, it's flat. So since this is velocity, the velocity is not changing. And acceleration is a change in velocity. That's all they have to remember. There's no calculating. Okay? It's just interpretation. All right. I want the total distance traveled. That's the shapes, okay? And this is why. Because average velocity equals distance, or sorry, well, average speed equals distance over time. So if I want to get distance, I go average velocity multiplied by time gives me d. Well, I've got the velocities on here. It wouldn't be hard to figure out the averages, okay, and multiply them by the time. So I'm going to take this shape right here where the velocity changes. The average velocity between 10 and 5 would be what? 7.5. Okay. Now, because we're doing yeah. Okay. So we'll go with our the height of our triangle, and the height of our triangle is actually only what? It's actually only 5 here. Okay. So we'll just calculate our areas, okay, and we'll run with it from there. Okay. We'll calculate our areas, add them up, and we've got our total distance traveled over the whole trip. Okay. Everyone follow me there? So it's like base times height over 2 for our triangles, base times height. We got one big rectangle here. We don't have to do two separate calculations. We could just do this whole rectangle, okay, in here. All right. Everybody with me on that one? Okay. All right. And that's really all you can get from that kind of graph. You can either get displacement or you can get acceleration, and that's it. You can actually get more off the position time graph, or I can ask you for more off of that. Okay? Did that answer your question, Megan? Yeah. Okay. What else, guys? Come in. A heat pump and a heat engine. Okay, so a heat engine uses the second law of thermodynamics. So as heat is going from hot to cold, okay, so here's the hot area, okay, here's the cold area, not gold, that's cold, okay. If I put the engine right here, heat and matter go through it and cause it to turn and do whatever it's supposed to do. A heat pump, okay, a heat pump is doing this. It's pumping heat from the cold area to the hot area. Okay, so this can do work. This requires work. Okay, so a heat pump uses energy, whereas a heat engine harnesses it. Okay, so the heat engine can do work. Okay, but the heat pump has to have work done to it. It's got to use energy in order to move against the second law. Okay, so if you're going to circumvent a law of physics, you have to use energy to do it, if it's even possible to circumvent it. In this case, it is. Okay, we can use energy to pump. It's like active transport. Okay, a heat pump's like active transport, whereas that's more, the heat engine's more like diffusion. Okay. Yep. Any other questions? A law of conservation of energy question. Okay. All right, so I've got a box at the top of this ramp. Let's say the box is 10 kilograms, not that you need that number. Okay, and let's say that it is stationary at the top of this 10-meter ramp. All right, I want to know how fast it'll be going when it is in this position, which is 4 meters above the bottom of the ramp. Okay, so I'm holding the box at the top of this slippery ramp. Okay, when I let it go, that's kind of when the question starts. So it has what kind of energy at the beginning? It's got some potential. Okay, is the energy here and here the same? The total mechanical energy is the same, yes, because only gravity is doing anything here, right? We're not pushing it up the ramp. Okay, so EI equals EF. Okay, initially, we've said we only have potential because we've outlined that I'm going to release the box. It's not moving at the beginning. All right, so I have initial potential, but no initial kinetic. What about at the second spot? I have both. Okay, there would be both kinetic and potential there because it's still above the bottom of the ramp, and I'm being asked to calculate how fast it's moving at that point. It would have no potential energy if the end spot was at the bottom. Yeah. Okay, so I want to get these expanded. So mghi equals mghf plus 1/2 mvf squared. And this is what I'm looking for. So what do I do with this term right here? Subtract it over to the other side. Okay, so that's going to leave me with mghi minus mghf equals 1/2 mvf squared. Okay, I can take the masses out because I don't need them. And now what do I do? Divide by 1/2 and square root. Okay, so now I've got VF. All right, now I can just plug in my numbers. So I'll have 9.81 times 10 minus 9.81 times 4 over 1/2 square rooted will give me my final speed. I know, that's what 9.81 times 10 is. Whoops. 58.86 5 square root. Okay, so it's going to be moving at 10.85 meters per second, 5 meters above the ground, or 4 meters above the ground. Okay, does that make sense? They all work pretty much the same way. Okay, any other ones? I'm not giving you a thinker. 2 decimals at the most. Yeah. Okay. And I mean straight up in the air when I say up in the air. Okay, so I'm throwing this rock up in the air at 15 meters per second. I want to know how long it'll take for it to reach a velocity of 15 meters per second down. Okay, so I'm standing on the edge of a cliff, and I go like this. I throw it up in the air, and then I move out of the way. So it's got room to fall below me. Okay, because if it was just me standing there, it would never reach, well, actually it would reach negative 15 by the time it came back to me. All right, so what am I looking for? I'm looking for time. How long, right? Okay, what am I given? I'm given initial velocity. What else am I given? Final velocity. Is it important that I indicate those are positive and negative? It sure is, because if I don't put them that way into this equation, it's not going to work. What else am I given? Gravity. Unless it says I did this experiment on Mars, you assume I did it on Earth, where g equals negative 9.81 meters per second squared. That would be where people would screw that question up. They'd probably get that the final velocity was negative and the initial velocity was positive, but they would forget to put the negative on the acceleration. That would be the spot people would screw that one up. And if you screw that one up, the question won't work. Because it's impossible for an object accelerating upwards to ever reach a negative velocity. Agreed? Yeah, your calculator will just go, error, can't do it. All right. So, here's what I've got. A equals VF minus VI over T. And I'm trying to solve for T, so what do I do with T? Now what do I do with A? Okay, and VF is negative 15 minus 15 over negative 9.81. Okay, so we've got negative 30 on the top divided by negative 9.81 on the bottom. So that's going to take 3.1 seconds. Or 3.06 seconds, whichever. I mean, guys, I'm gonna know. If you write all your decimals down, I'm gonna know you did it right. If you round off, just make sure you keep at least 1, probably 2 decimal places when you're doing this, because gone over significant digits. We don't do that till physics and Chem 20. Okay, it's easy, but we just don't do it in Science 10. All right, so does that one make sense? Acceleration? Okay, what else, guys? Yeah. In the multiple choice, I think I have 2 questions where I ask about people. So enough that you could recognize it's what they did. Okay, like a work energy theorem question? Okay. Okay. So it's a work energy theorem question because that's what Seb asked for. But we know that it's a work energy theorem question because it asks for force, and the only thing we've associated force with so far is work energy theorem. Okay. It also tells me a distance, it gives me a mass, it gives me a speed, and there's an indication here that work is being done. We know that when you pull back a slingshot, you're doing work. Okay. We know that the rock would be accelerating from 0 to 14 meters per second, because that's what would happen when we release the slingshot. So we know there's changes in energy going on in the context of this question. Agreed? Okay, and that's what we have to get out of it. So our givens are, okay, distance, 0.35 meters, okay, mass, 3.5 kilograms, VF, 14 meters per second, VI, 0 meters per second, okay, and we're looking for F. Right. So work is a change in kinetic energy in this question. Right. So force times distance equals EK final minus EK initial. And what's the initial kinetic energy in this question? 0, because the rock is not moving when it's being held in the loaded slingshot. All right, so force times distance equals 1/2 mvf squared, and I'm looking for F, so what do I do with D? All right, so we've got 1/2 times 3.5 times 14 squared over 0.35. All right, so I think we're going to have kind of a big number for force here, but that's all right. Whoops. Okay, 980 newtons. That's a lot. That would be like I put the slingshot and hang it from the ceiling, and then I grab onto the slingshot and hang from it while holding another 30 pounds or so. It's a little ridiculous. Okay. Yeah, you wouldn't want to be standing in front of that slingshot though when that rock came out of there, because the rock is almost 8 pounds, and yeah, it would be moving kind of fast. Yeah, leave a 3-foot hole coming out. Okay, wouldn't want to be in front of that one. All right, any other ones? Kenneth? No. No, no. I just I was debating whether I should tell you or not. And I just said, whatever. No. You don't have to do that. You won't have to calculate instantaneous velocity from a curve. Any other ones? Okay, well, that's good. You guys had way more questions than period 1. You know how many questions period 1 asked? 0. Okay, so you guys got a lot more out of this than they did. Okay, so you've got another 25 minutes or so. Okay, work on that handout. Okay, do whatever else is going to help you prepare for tomorrow's test. If more questions come up, then we'll go over them. A couple of other things here, guys. Just note for the rest of the semester, because that's not very much time anymore. Okay, during period 1, because I had time, because they didn't ask me any questions, I was able to sit down and plan out the whole last unit and how long we needed to get things done, whatever. So I have, and your unit exam for unit 4 is June 15th. I gave you 2 weeks, almost 2 weeks notice. Okay, 1 day less than 2 weeks notice of that unit exam. Because what we're going to do is, in the 7 class days we have after the exam, that's all we'll have, 7 days, okay, we have to go over about 10 lessons. So that's okay. I've been able to, well, I took out the lab, so we won't be doing that. I made the activity that we need to do a little less labor intensive, and then basically everything else will go through kind of, so there'll be a lot of me talking and you listening on a couple of the days. Okay, so Thursday, after we go over the test, we'll do the first lesson in the unit. Friday, you'll start the 3rd lesson in the unit, but you won't finish it because it's long. We'll finish it on Monday and go over the 4th lesson in the unit on Monday as well. On Tuesday, we will go over the activity that I made less labor intensive. Wednesday, we'll go over latent heat and heat capacity. Thursday, we'll go over biomes. Friday, we'll unit exam review. Monday, we'll unit exam. And then we'll have 1 day for final exam review. And that'll be the Tuesday. Okay? So, I will give you guys the final exam review package next week, early next week, so that you have it and you can start looking it over, so you know what kind of things you want to ask on that last day of classes. Okay, or if you choose to come in during the exam periods to ask questions, that's fine as well. All right. Okay. Get to work.